Okay, this is Emergent States of Matter for the week of Monday, March the 8th, 2021. And let's start off by recapitulating where we were last week. So last week we quoted the result, which you're going to derive in class, in homework, excuse me, that the normal fluid density has a behavior that goes as temperature as T to the 1/4. And at the end of last lecture, we talked about, well, what happens, is the normal fluid density the same thing as the number of particles that are not in the condensate? In other words, the number of quasi-particles. And the answer is no, it isn't. And so how did I didn't tell you why, I just told you how one can calculate that. So what we have over here is the depletion of the condensate. In other words, the condensate is all the particles that are crammed into the ground state, uncomplaining, since they're bosons. And so n minus n naught is the number of particles in the not in the condensate, and then the ratio is the depletion. So you might think that the fraction of particles that are not in the condensate would be the same thing as the fraction of particles in the normal state, or the normal fluid, and so therefore you might anticipate that the depletion would be the same thing as this quantity rho n that we've derived. And the big shock is that that's not true. Okay, that when you compute the depletion, which you're going to do in the next homework, you'll see that it goes as T squared, rho n goes as T to the 4th. So they have a different temperature dependence. So the point about this is that when we talk about rho s and rho n, we think of those things as superfluid density and normal fluid density, but really they are defined phenomenologically in terms of the ways that they go into the in the two fluid model. They're not the same thing as the simple idea of a particle being in one state or another. And the reason for that difference is that these are all collective properties of the system. And so when we compute the quasi-particles, we'll see that quasi-particles are literally made from every actual atom in the system. And so we've emphasized this difference before in the class. We also talked about the chemical potential of the quasi-particles being 0, and the chemical potential of the helium atoms being minus 7K, completely different, because they are different types of entity. And so that's an important part of the message of this idea of emergent states of matter, where you have elementary excitations of the system that are really many body aspects of the system and cannot be simply related to one particle or another. And then the other thing that we talked about at the end was that if I write down the Hamiltonian for the two fluid model, which is what I have written over here, so we think of it as having a term, a half rho s vs squared. You would just say, yes, it's just the kinetic energy density of some superfluid component, nothing special about that. Why would you think there's anything special about it? But when we put in the formula that the velocity is given by the gradient of the wave function, then you can see that what's happening here is that the energy is given by the formula. Let me write it out more neatly over here. Energy is the energy of the normal part plus 1/2 rho s vs squared, which is equal to the energy of the normal part plus 1/2 rho s h squared over m squared grad gamma squared, where gamma is the phase of the wave function. And so that's where we ended last lecture. And so the point about this is that you can see then that the superfluid density is actually a stiffness. So what kind of stiffness is it? Well, what it is the following. Let's suppose that I have the spin, not the spins, the order parameter over here and the order parameter over here. Well, of course, there you go. Okay, finger and pencil. All right, now what's so special about this? Well, what this says is that if I introduce a change in phase between, say, my finger, the order parameter over here, and the order parameter where my pencil is, then what happens is that change of phase, that's a slowly varying gradient of the phase of the condensate wave function as you go from here to here, that raises the energy of the system, and so it costs energy. Just like if I have a bunch of springs and I stretch them, I extend the distance between them, and that causes a change in the energy of the system. It raises it, and the stiffness coefficient is the spring constant K, just like you have in Hooke's law. So what this says as an interpretation. So here is space. Let's draw the phase of the wave function gamma like this over at this point. And then let's say at this point, so this is x1, this is x2. Let's suppose at this point gamma is something different, like so. Then along the way, the phase gradually varies until it gets to over here. And the point is that this configuration costs energy. And how much energy does it cost? Well, that is proportional to the gradient of the phase squared, and it's important that it's squared because that means it doesn't depend on the sign of the phase, and so therefore there's a coefficient that comes in here, which is something proportional to rho s, and so this is analogous to the energy is 1/2 k x squared in the spring, where k is the spring constant and x is the displacement. And this could also be, say, the Young's modulus in a material as you stretch it and so on. And so what we've learnt from this is that the helicity, the superfluid density is actually a stiffness. And so it's an elastic modulus, more precisely. And so that means it's sometimes given the name of the helicity modulus. And so what we can see then is that rho s is then an example of an emergent rigidity. And so the idea that we have an emergent elastic constant, this is an example of generalized rigidity. So in my view, the most important thing about emergence and emergent states of matter is that you have an emergent rigidity. You get a kind of collective behavior of the system, which didn't exist before, as a result of being in this collective emergent state. And as we'll see, this is a many body cooperative effect, and is a generic hallmark of emergence. Okay, so that's the where we ended last lecture, a bit more of a recap. I want to also make one more comment before we go on about long-range order and the special case of 2 dimensions. So let's do that. So let's just recapitulate what we've learned about superfluidity. So this is so I'm making this comment really just to summarize this section. So what we've learned is that in a superfluid we have off diagonal long range order, and that tells us that that gives us the emergent rigidity and superflow, etc., topological defects, okay, and so on and so forth. So what does it really mean? So remember, we talked about the long range order part. So let me now tell you a fact about long range order that I haven't really emphasized so far. So what we know is what happens in 3 dimensions is something like this. So in 3 dimensions, we have that for t less than t lambda for d equals 3, we know that there what happens is we get n naught over n, and the limit as n goes to infinity is non-zero. So we have a condensate. So that's a sort of naive picture of the condensate. The way we wrote it down was in terms of the 1 particle density matrix, which looks like this. And what we saw was that for r minus r prime going to infinity, we argued that n naught over n, or n naught over v, if you will, is non-zero, and so that as you go to large separations, the 1 particle density matrix goes to a non-zero value, which we call n naught over v. What I didn't tell you was that the way that it approaches that, as you might probably have guessed, is that it goes as an exponential. So it goes as e to the minus some r minus r prime over some correlation length, which I will just write like that without any further explanation. And so what you have is a exponential decay of this type of correlation function for the field operators, but it goes to a non-zero value. So let's draw that over here. This is distance. This is rho of r prime, and so what we know is that this thing behaves like this. It starts off at some value, and then at large distances, it goes to some non-zero value, and that non-zero value is what we think of as the n naught over n, the non-zero value. So this is true for t less than t lambda in three dimensions, like so. Now, you might ask, and of course, what happens above t lambda? So let's just draw that in for completeness. So if I were above t lambda, then we don't have any long range order, and so it just goes to zero like this. So this is a exponential decay. And this is also an exponential decay. And what happens below not below, above the lambda point is that it goes to a value which is equal to zero. And because it goes to a value which is equal to zero, then we say that there is no long range order. So the fact that this thing over here is non-zero means that we have long range order. Ah, what happened? Man, that's scary. Okay, nearly lost my whole lecture. Okay. All right, so there we are. So that's what happens. This is true for d equals 3. Okay, so now I want to tell you what happens in d equals 2. So in d equals 2, what happens is roughly speaking, you can have superfluidity without Bose-Einstein condensation. And so what do I mean by that? So as you know, in d equals 2, there is no Bose-Einstein condensation in 2 dimensions, at least no ideal Bose-Einstein condensation. So that means that so ideal bosons do not condense for t greater than 0 in 2 dimensions. As a matter of interest, is there anybody in this class who doesn't know that? So there's several people, 2 people raise their hands, and both of them do not know that the transition temperature for Bose-Einstein condensation 2D is 0. Is that right?
Yeah, I haven't seen that before.
Anybody else not seen it before?
Me neither.
I haven't either. No.
Oh wow. Okay. You're supposed to have done stat mech beforehand. Okay. All right. Then that's going to be on the homework. All right, you need to know this. Okay.
Oh, sorry, I just remembered that I have seen it. So
Okay. Yeah. Okay. But okay. It sounds like I need to include that on the homework. So I will put that on. Okay. It's you know, everybody's had. If you've been to my stat mech class, you will definitely know that result. Okay. So what that means is that for t greater than 0 in 2 dimensions, if I look at the limit as n goes to infinity of n naught of t over n, then that is equal to 0. But my claim is that something funny happens. This is non-zero. In other words, the helicity modulus is non-zero, again, with t less than t lambda over 2. So what does that mean in terms of sketching the behavior? So let's draw that. So what that means is the following. So if I now draw this graph over here, so here I'm going to draw R prime, and what I'm going to do is draw the behavior like this. So okay, so it goes to 0. So the first thing you can see from here is that the asymptotic behavior is that rho of R prime tends to 0. So that's the first thing. But the surprise is that this behavior here, this functional form, is an algebraic decay. Or sometimes called power law decay. And not exponential. And so if I write it down in terms of the equations, what it says is this: in d equals 2, what we have is rho of r and r prime asymptotically for large r minus r prime behaves like 1 over r minus r prime to some power. I'll call it, I don't know, whatever, sigma of t. And this is true for t less than t lambda of 2. So in other words, my claim is that the one particle density matrix decays as a power law, and so actually the power law turns out to be temperature dependent. And excuse me. And what happens above Tc, above T lambda? Well, of course, it also goes to 0, but it goes to 0 exponentially. Like so. And so and I don't know if I said this over here, but let me rewrite history just to be crystal clear. If this is true for t less than t lambda of 3. And if you ask, well, what happens when t is greater than this, then it just goes as an exponential decay when t is greater than t lambda. And so I've put little pluses and minuses on the correlation lengths to show you that the correlation lengths are in principle different above and below the lambda point. So in this case here, we don't have this decaying to a constant, and that's what I've drawn over here. Okay, so back to our two-dimensional case. So what you see happening then is that in 2D, the superfluid transition is a change from exponential decay of a correlation function which is essentially what rho of r and r prime is. Because this thing is psi of r like so. So it's a change from exponential decay to algebraic decay. Not a change from a 0 to a non-zero value at large separations. So that's the that is the difference. So so you'll demonstrate that. So this will be seen in homework in one of the later homeworks. The other thing is this power law decay is true for all temperatures less than the two-dimensional lambda point transition. This symbol here means for all. And so this is not the same thing as just the power law decay that you see at a critical point. And the reason is that that we see this power law decay for all temperatures less than T lambda, whereas the critical phenomena power law decay happens exactly at the critical temperature, in other words, only at one point. And so we're going to see that this feature is also a generic aspect of spontaneous symmetry breaking. Okay, so now we have understood that. So I think we're going to move on now to the next topic, unless there's any quick questions.
I have a question.
Yeah, go ahead.
So what we were just talking about is off-diagonal long-range order. So that's like measuring the probability that if there's a particle here, then there's also a particle this far away from it. Right before this, we were just talking about.
No, that's not true. So that would be a two particle density matrix. So the off-diagonal long-range order is it comes from the one body density matrix, right? So let's go back and just remind you about that. This is a very important point. So I'm going to zoom back about 1 million years. Where did we do it? Somewhere back here. All right, definitely somewhere around here, right? Yeah. Okay, so all right, so what I want you to, why I took all this time to wind back, what I want you to notice is this. When I write down this, it's a single particle density matrix. So it's not saying here's a particle over here and a particle over here. That's what you would call the two-body correlation function, say in classical StatMech. But here we're looking at a correlation function between a field operator and its conjugate. So we're looking at an object that is only one particle. I mean, remember, a density is a creation operator dagger times an annihilation operator, right? A dagger A, right? That's a number. So if I want to compute a density, I would have to have 4 of these psi operators to have a two-body correlation function. So this is why this is called a single particle density matrix.
So I should be thinking of psi dagger and psi as annihilation and creation, or switched around.
Yes.
Or is that wrong? Okay.
Exactly. They're field operators that are annihilation and creation operators, but in real space as opposed to in momentum space.
Okay.
Right. But the correlation, what we're looking at, is the correlation between an amplitude of a field and the amplitude of a field at a distant point in space. And that's why this is quantum mechanical, because you've got these off-diagonal terms, which you wouldn't have if you had an observable, like, say, the number operator.
Okay. So my question is, so this is, what is the difference between having off-diagonal long-range order and having the phase coherence that's implied by the stiffness that we were talking about immediately before this discussion?
The stiffness is a consequence of the off-diagonal long-range order.
Okay. All right.
Okay, so let's go back to where we were, somewhere over here. Okay, so let's now move on to the next topic. So the next topic is section 3.4, and this is a really fun section. So we're going to now put in interactions. So up to now, we've really been able to do a lot of things. We've learned a lot of concepts, but we didn't do anything technically hard, or nothing very much compared to what you've already seen in your graduate StatMech class, hopefully. So now we're going to really make a quantum jump in technical difficulty, I would say. We are going to literally do a detailed many-body calculation using quantum field theory, but don't be scared, because I will hold your hands and we'll get through this, and it will be as painless as it can be. And the upside of it is that you will learn a technique which is quite simple. You can do this all with high school algebra, and yet it does a very sophisticated type of calculation that would require a huge amount of quantum field theory and the normalization group to really do in any other way beyond perturbation theory. So it's actually very, very cool. And this will enable us to also solve the problem of superconductivity as well. So the goal here is a model of an interacting Bose gas. So that's the model. The ultimate thing we want to achieve is we want to show how to construct a quasi-particle. From the bottom up. So up to now, we talked about it in a top-down way. We wrote down the energy, we wrote down the two-fluid model. I pointed out that we have some off-diagonal long-range order. I pointed out that therefore we can interpret the superfluid density as a helicity modulus. And so we have a very sort of vague, woolly idea of quasi-particles. We have an idea about topological defects, but we don't really have a way to like calculate and see that any of this is actually true. So we want to construct this from the bottom up, from a microscopic calculation, and to see if our phenomenological picture is really true. So the difficulty is that we can't calculate in general for superfluid helium because of strong interactions. And so that means that what we're going to do is we're going to just say, well, the interactions are weak. And so that was just really a theoretical exercise until about 20 years or so ago, when it was discovered how to make such weakly interacting Bose-Einstein condensates in the lab. So this was until the late 1990s. This was a theoretical fiction, I suppose you could say, but now realized in the huge field of cold atomic condensates. So that's the calculation. So let's talk a bit more about why I think this is cool. So again, still talking about our goals here. The method that we're going to use is a fast way, I should say, to do some serious quantum field theory, but using elementary methods. And the other thing that's really cool about this is that it's not just perturbation theory. So most of your life you've been doing perturbation theory. This is going to be beyond perturbation theory, but why it is beyond perturbation theory is not going to be obvious to you. I'll tell you later on. So another way to do this would be to use a renormalization group and other kinds of very sophisticated methods, but we're going to avoid all of that by some nice shortcuts. Okay, so that's the method, and then why am I teaching it to you? So later you will use this to solve the BCS model of superconductivity. And that's going to be a one or two homework sets that it'll take you to do that. But it's not as bad as it sounds. I mean, you know, it's perfectly reasonable in the 21st century to give as a homework set something that won a Nobel Prize when it was first done 50 years ago. So you'll see that you're able to do it using these methods. Okay, so let's start off with the Hamiltonian. So we're going to have a bunch of spinless bosons. And the Hamiltonian is going to be written down like this. So sum over K, I'm going to just write it down in second quantized form. So there's the kinetic energy, which you've seen before. And now I'm going to write down the interactions between the particles. And so the interactions between the particles, I'm going to write like this. So this is the Hamiltonian. This factor of 1/2 over here is to avoid overcounting. So when particle R interacts with particle R prime, that's the same thing as particle R prime interacting with particle R. And the energy spectrum that we've assumed here is this thing is just the energy spectrum for ideal bosons. And this term over here, we're going to come back to this later. This is just what happens when I sum over I and J of the potential energy between a particle at Ri and a particle at Rj. So this is just simply the two-body interaction energy. Okay, so what I'm going to do now is I want to write this formula in terms of field operators. So what we're going to do is our strategy is write this in terms of field operators. So we're going to partially do that, and also work out you know the interaction terms. So and one of the things that I'm going to show you and help you understand is what you may have heard before in quantum mechanics, known as a normal ordering. which we'll see is related to the problem of self-interactions. Okay, so I'm not going to write down the second quantization rules. We know that we have field operators, which I've defined for you before. So let me just write them down so you have them. Okay, so those are the field operators. So we know that the annihilation creation operators satisfy Bose condensation, Bose commutation relations. So we know that AK prime is equal to AK dagger, AK prime dagger is equal to 0, and we also know that AK dagger prime is equal to delta of KK prime. And I may forget to write things as vectors sometimes, but you should know which things are vectors and which things are not. Okay, so then this is a statement that you can prove yourself. So the field operators satisfy the analog, so but in real space. So psi of r prime is equal to psi dagger of r prime is equal to 0, and the commutator of psi dagger of r prime is equal to the delta function, but now it's the Dirac delta rather than the Kronecker delta. And if I want to know what is the density at any given point, so the density operator is then this operator rho hat of r is equal to psi dagger of r psi of r. So that's the operator that appears over here. Okay, so what I think I'll do is I'm going to, I want to make sure that you don't get lost. And I think there might be a danger of that. So I want to go a little bit more carefully about how you construct these operators, just to make sure that you are on the same page, and so we can follow the next thing. So so I think what I'm going to do is I'm going to demonstrate these points for you, rather than leave you to do it yourself, because I think it's important to make sure this is correct. So the first thing I want to explain is that the field operators, psi of r dagger, these are annihilation and creation operators in real space. Now you may think, well, it's kind of obvious, but let me show you really why it's true, because you'll need this in some of the calculations that you're going to need to do. So let me first of all write down for you what is a position space wave function. So a position space wave function says I've got particles and a bunch of positions like so, and so this says if I know where the particles are, write down the wave function for me. So there it is. It's that ket. And so my claim is that this is how you get that. You start off with a vacuum state, and then you act on it with a particle at Rn, and then a particle at Rn minus 1, etc., all the way up to something like this. And then you normalize this by 1 over the square root of n factorial. So that's my claim. So let's see what this means for us. So let's suppose now we ask, what happens if I take a field operator that creates a particle at R and have it act on a wave function or a state that has particles at these n positions. So let's make sure that we understand this. So this part over here represents a state at Rn. We don't say which particles they are because they're identical bosons. And so that's why we have this factor of the square root of n factorial over here, because we can permute them in any way we like. Okay, so let's ask what happens when we add this state to here. So what's going to happen is that you're going to get now a new state, which is the original particles at Rn, but now I've added a new particle at the position R. So this, so the point is you tell me what R you want, and then that R gets added to this ket. It originally had n particles at R1 up to Rn. Now it has an additional particle at the point Rn, and there's going to be a prefactor in front of here, which from the Bose creation operator identity gives you a factor of the square root of n plus 1. So this is kind of like this operator. If I have a k dagger acting on a state with particles in plane wave states, then that is just nk plus 1 acting on the state n1, nk plus 1, like so. So it really just comes from that identity. So that's what happens when you add a particle. Now, when you subtract a particle, it's a bit more complicated because you can subtract many different particles. So let's see what happens then when I take the operator psi of r and act that on the state Rn. So what's going to happen is, well, I can say, well, there's lots of things that I could do. For example, if there's a particle at R1, then I could take that one away. If there's a particle at R2, I could take that one away. But that will only be true if R is the same as one of these things here. So you might say, well, the first state that you might get is this state, R1 up to Rn minus 1. So this is a state where you now have n minus 1 particles in the state, not n. So you've certainly removed a particle. So this is what you've done here. You've subtracted a particle with this field operator, but the particle that we've removed is the particle at Rn. And that can only be true if this R is equal to Rn. So what I need to have here is a prefactor which says that R is equal to Rn. So if this, so in other words, if you tell me what this value is, then that is the same thing as goes in here, and that delta function kicks in, and so I can remove the particle. If the particle isn't at Rn, then I can't remove it. So that's why we have to have that delta function here. So then the next term you might say as well, that's great, but I could also have taken away a different particle. So I could have taken away the particle at Rn minus 2, and at Rn minus 1. So then I would have Rn minus 2, no particle at Rn minus 1, and then the particle is Rn. So this would be true only if the delta function, if R was equal to R of n minus 1. And so on and so forth, all the way down to delta of R minus R1, the state with n minus particles in it, but they start from R2 rather than from R1. So that's what can happen. That's the different ways that I can take particles out of the state, and then I've got to normalize it. And so the normalization is going to be a factor 1 over the square root of n, as you can check, in order to make sure that this thing is normalized. And it's like that because there's n terms here, and each of these kets are orthonormal. Okay, so that's the first thing. So that's the effect of taking away and adding particles. Now, the next thing I want to show you is that the density operator I want to prove that rho is really psi dagger of R, psi of R. So I want to prove that, and I also want to show you that this thing has the correct interpretation as a microscopic density. Now, those of you who took my 504 Stat Mech class, and I've mentioned this before already, you know what the microscopic density should look like. So what we're going to expect is that this operator should look something like this. The density operator is just the sum over particles like this, the sum over delta functions of particles at the positions of all the n particles. That's what we mean by the microscopic density. So let's see if it's true. So I'm going to show you that now using the behaviors of the field operators that I've shown you. So the way I'm going to prove this is like this. I'm going to consider any two n particle states, which I'm going to call phi and phi prime. Okay, so they're just two states like this. And what I want to work out now is the expectation value of this operator, this rho. So we're going to compute the expectation value of the matrix element of rho hat of R. So let's go and write that down. And what I'm going to do is I'm going to use the trick that you saw in elementary quantum mechanics of inserting complete states into a matrix elements. So the thing we're going to start off with is this matrix element. So we're just going to write it down like that. And so what the strategy is to insert a complete set of states in between the field operators that go into this. So the claim is that this thing should look like the following. So let me write it. I'm going to split this up into different colors so you can see what I'm doing. So this is going to write down as phi prime over here. and then the field operator, rho is meant to be this product over here on the left. So I'm going to write down psi dagger of r over here, and then another psi of r over here, and then phi. So that literally is what this thing is. And so what I'm going to do now is I'm going to insert into here a complete set of states. And what that means is I'm going to insert, when I say insert a complete set of states, what that usually means is I have some states and then I use this identity from quantum mechanics. If I have some states, I take this operator that is just equal to 1. That's just the completeness relation that you learned from ordinary quantum mechanics. So the question when you say insert a complete set of states, what you're always doing in stat mech or quantum mechanics is you're expressing 1 in some cleverly chosen way. Okay, so that's what we're doing here. So the way that I'm going to do it is I'm going to write it like this. I'm going to write it, actually not over there. I'm going to write it over here. I'm going to put phi prime, psi dagger of r, and over here, psi of r, phi. Okay, so that's my matrix element. And then the thing that I'm going to insert in some sneaky way is I'm going to put in a complete set of states here, which are n-1 particle states, R1 up to Rn-1, R1 up to Rn-1, like that. And then I've got to do the sum over n. Well, these are states which are defined as particles in three-dimensional space. So then my sum over states is then the sum over the positions of all the particles, which means I integrate over all the particles position like that. And I remember that these are n particle states, not n-1 particle states, not n particle states. So those are n-1 particle states. On the other hand, these things over here, these are n particle states. Okay, so now let's go and do the calculation. And what we have to do is simply use the result that I showed you before. So what we're going to have is the psi dagger acting on the n-1 states to the right of it, and the psi acting on the n-1 states to the left of it. So my claim is that this thing is the following. So I have this. Now I have my phi prime, and now what happens is when psi dagger acts on the state to its right, it's going to create. Where is it over here? It's going to create an extra particle, as we can see over here, and a factor of the square root of n+1. So what that's going to be then is what we'll have in here is R1 up to Rn-1 as we had before, but now I have the vector R that we didn't have there before. And that vector R is because this thing here is the same as that R that was over there. And then, of course, I have a factor of the square root of n, because I have the factor of the square root of n, which came from the square root of n plus 1. Well, I've got n minus 1 particles, so n plus 1 when n is n minus 1 is just n itself. So that is this thing acting onto this. Now the same thing happens with the psi operator acting to the left, because an annihilation operator acting to the left is like a creation operator acting to the right, because they're Hermitian conjugates. So then what I'm going to get for the other one is I'm going to get for this one over here, let's draw this in orange so you can see the difference. So this is going to then give me another factor of the square root of n, and then it's going to give me r1 up to rn minus 1, and now I have r again, and then this times 5, and let's change the color. So I have this, and so now let's look at what this thing is. So this would be the same thing. So notice here I have n minus 1 integrals, but over here I have n position vectors. So what we're going to do is we're going to convert this n minus 1 integrals into n integrals plus a delta function. And why is that? Well, if I have an integral with a delta function, the delta function just kills one of the integrals and just gives you one thing left over. So this thing I can write as the following. I'm going to call the r Rn, like so. And then over here, I'm going to have, again, R1 up to Rn, and then my phi, like so. And so what I've done is I've changed this R over here has now turned into an Rn over here, or maybe it was R1 over here. It doesn't matter, whichever one I wanted. So therefore, what I've done in order to do that, I've added an extra integral, and so I have in here now a term R minus Ri, and because I've got these n, this is equal to n, so I've got n terms, so I'll just write the n terms as the sum from I equals 1 to n of this delta function here. That gives me, all the terms will be the same. And then the last thing I have to do is I have to do my integral over my complete set of states. So I have to have d3r1 up to d3rn. And so what I've done is I've now got a formula which has got manifestly n particle states, R1 to Rn and phi prime, sandwiched between having matrix elements, so they're non-zero, they're not orthogonal, and so this I can write as phi prime rho phi, where I can just read off that rho is the sum from I equals 1 to n of delta of r minus ri. And this is exactly what I wanted to prove. This is the this is the microscopic density. And so we're done. Okay, so that'll take a bit of unpacking for you. I expect you may want to watch the video of that and go through it in your own time. So now that means that I can write down the number operator. There's just n is the integral d3r of psi dagger of r psi of r. So I take the density and integrate it over space. Then I'm going to write down the, I'm going to define my Fourier transform, because everything, the key to not getting lost in any of these things is to make sure you remember what your Fourier transform is. So our Fourier transform is f tilde k is equal to the integral d3r e to the minus I k dot r f of r, and f of r is equal to 1 over v, the sum over k e to the plus I k dot r f tilde. Okay, so that's how I'm defining Fourier transforms. Okay, so you have to make sure that you know that. So then my claim is once I have that, I'm nearly finished. Once I have that, then my claim is this, that I can write down the density operator as rho hat of k. So the Fourier transform of rho of r, rho hat of k, is equal to the sum over q of a dagger k plus q aq. Okay, so notice that here you tell me what k you want, and that appears over here. And similarly, this variable, this q, this is a dummy variable, which is summed over on the outside. So this formula here tells me how to write down the density operator. So now that I know that, then I can write down the formula for the Hamiltonian of the system. So the reason we were doing all this was we started off with our Hamiltonian as being what you can see over here, and now we want to write this term down in terms of field operators. So let me write down for you what the answer is. So our goal to finish is to write down the interaction Hamiltonian in terms of field operators. And all we have to do is substitute into the formula that I wrote down before. So the interaction Hamiltonian is then 1 over 2v, the sum over v, u tilde of k, the tilde denoting a Fourier transform, and then the density k, the density of minus k, or if you like, the density complex conjugate. So that comes just because the formula for the Hamiltonian, this thing here is a convolution. Okay, so So now I have this, then I can write this down in terms of field operators. And this is going to be the last thing I'm going to write down for today. So then this looks like in terms of field operators. So now what I'm going to do is I'm going to substitute in what rho actually is. So this, we're going to use this formula here and substitute it into this formula for interaction Hamiltonian, and that's going to be the last thing I write down. So we're going to have this H interaction is equal to 1 over 2V sum over K. So it's got to be a sum over K because that's what it is. Then there's going to be two dummy variables, and I'm going to call those dummy variables Q and Q prime. Okay, so those are going to be dummy variables. Then I have my Fourier transform of the potential. So that's the U tilde of K. And then I've got two factors of rho. So I've got one factor over here, another factor over here. Each of these rows has got two annihilation and creation operators in it. And so I'm going to have a product of 4 annihilation and creation operators. And let's write those down. So this is going to be times over here, AK plus Q dagger, AQ, and then A dagger of Q prime minus K, A Q prime. So those are my 4 operators, and then the dummy variables Q and Q prime are summed over, and then the K is the thing that is the formula in here. Actually, I can see a little typo over here, so that's really meant to say sum over K. So there we go, like so. Okay, so next time we're going to take a look at this formula, and we're going to realize that it has some kind of infinity in it, and so we will deal with that. Okay, so I'm going to stop here. I'm going to stop the recording.